Hello friends, welcome back. In this video, we are going to talk about understanding and comparing the graphs of sine and cosine and beginning to understand why we call them circular functions. So one of the best ways for us to understand and create a graph is to first make a table of values. So I've set a table up here for us. We have an input x. In this case, x is going to be actually s, that arc length in radians, and we're going to find sine of that arc length. So essentially, we're just going to find all these values on the unit circle. We know all of these values, and we know these values because we know and understand how to use our unit circle. So I'm going to calculate sine of 0, sine of pi over 6, etc., all the way down. I'm going to list those values, and then we're going to plot them on this coordinate axes here that I've drawn, and I've kind of spaced it out in a special way. We'll talk about how I've broken it down. So sine of 0 is 0. Sine of pi over 6 is 1/2 or 0.5. Sine of pi over 4 is root 2 over 2, essentially 0.7. Pi over 3 is root 3 over 2, which is about 0.86. And then at pi over 2, we get 1. So you'll notice between 0 and pi over 2, these values are increasing. Or essentially in the first quadrant, the values are increasing. So what happens in the second quadrant, going from pi over 2 to pi? So sine of 2 pi over 3 is root 3 over 2, or again that 0.86 value. Sine of 3 pi over 4 is going to give me root 2 over 2, or 0.7. Sine of 5 pi over 6, I get out 1/2, and sine of pi, I would get 0. If we look at what happens here, we'll now notice that we went from 1, the values became smaller, to 0. So in quadrant 2, the values were decreasing. All right, so I'm going to go ahead and just list our quadrantal values for sine of 3 pi over 2 and sine of 2 pi. We have -1 and then 0. So let's talk about graphing these. When we think about graphing our trig functions on our coordinate plane, we want that x-axis to be measured in radians. And we want to think about what's called one period, and we'll talk about that in a minute, but from 0 to 2 pi, or 1 full rotation. So quadrants, I've got pi over 2, pi, 3 pi over 2, and 2 pi. So each of these first two quadrants, I broke them up into pi over 6, pi over 4, pi over 3, etc. So I'm going to list those values on here. We've got pi over 6, pi over 4, and pi over 3. And it would continue going in this direction as well. We would have 2 pi over 3, 3 pi over 4, and then 5 pi over 6. Of course, that's really tiny and hard to write in there, so I'm going to leave those out. All right, so let's look at plotting these. So we're going to start at 0, 0. At my pi over 6 value, I go up to 1/2. At pi over 4, I go up to approximately 0.7. And at pi over 3, I go up to about 0.86, which is almost 0.9. Pi over 2, we're up at 1. That looks a little high. So you see we've got this nice kind of curve occurring here in quadrant 1. So let's look. We'll have something similar occurring in quadrant 2, but it's going to be going down. So, about like this. and goes down. So if we continued this pattern and continued making this table values, what we're going to notice is between pi and 3 pi over 2, we're going to go down to -1. So this curve is going to go approximately like this. Notice it's a nice smooth curve that I'm drawing. And then from 3 pi over 2 to 2 pi, around here, we're going to go back up to 0. So this is what our sine graph looks like. This represents one period. On my y-axis, I went up to a high value of +1 and a low value of -1. And we want to notice when we start talking about graphing, especially when you work on your lab, you're going to be asked to list these 5 key points. So we've got these 5 key points, which are my intercepts and my max and min values. And listing those, I've got 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and then 2 pi, 0. Now, of course, our graph doesn't end here because we can continue traveling in radians around our unit circle infinitely. So the graph continues and we kind of have this similar sort of pattern. So I've got these dotted lines here to show that my graph is going to continue down and then back up, similarly off greater than 2 pi. So what we're looking at here is one period of sine from 0 to 2 pi with our 5 key points. So these points that I've listed in red are what we call our key points. And those are important when we have to create a graph. So some characteristics that we might want to state about our sine curve. It has a domain of all real numbers. And the way we say that in trig is we say that those x values, those inputs, are from -infinity to +infinity. If you haven't had me as a teacher before, you may not have seen this symbol. This is an element symbol. It says x is an element of the set or the interval from -infinity to +infinity. We don't traditionally use this in our class, but this means the set of all real numbers that are. What is the range? The range are my set of output values. Where do my y values, or what are my y values bounded between? What is my highest y value and my lowest y value? So my y values are in the set inclusive from -1 to +1. Remember, when we're writing our domain and range, we always write these intervals, least to greatest, left to right. And because these max and min points are defined, they are points on the graph, we use square brackets. The period of sine, so that period that I've mentioned of a traditional sine graph with no transformations, the period is 2 pi. So what that means is this graph goes up and then down and back up. And it does that over and over again. So it would have another sine over here on the left. So what does that look like? So considering graphing this, and I'm going to divide this axis differently. I'm going to count 2 pi, and I'm going to add another 2 pi, another period, another 2 pi, which gives us 6. Another 2 gives us 8. I can continue doing this forever. My graph doesn't go off to the left, but I could say -2 pi here, and we've got 0. So we graphed one period, and we drew that graph. It went up and then down. We have this nice, it's hard to kind of make it perfect here. without graph paper, but we've got this nice sine curve. Again, you want to remember that sine is going to always be bouncing between +1 and -1. So a second period of that, it's going to repeat itself. We're going to have that exact same curve between 2 pi and 4 pi, and the same curve between 4 pi and 6 pi, same curve between 6 pi and 8 pi. Of course, this doesn't end. It keeps going forever. It also is going to do that same pattern in the negative direction. All right, so I hope this gives you kind of a better understanding of what our sine graph looks like. And again, it's periodic 2 pi. So this period repeats every 2 pi. It goes off to the left and off to the right forever. So again, that domain is all real numbers, and the range, it's always going to be bouncing between positive and -1. So my range is a closed interval -1 to +1. So let's look at the cosine graph. All right, what we graphed here, this graph was y equals sine of x. So let's look at cosine. So again, we want to understand the graph of one of these circular trig functions. Here we're going to focus on cosine. I've got the same table, and instead of plugging it into sine, I'm going to plug it into my cosine, or I'm going to be getting that output, the x value on my unit circle for each of these radian arc length measures. So I'm going to pause. I'm going to just write all of those values in to save us some time, but you should pause. Make sure you can determine what all of the cosine trig function values would be for these arc length measures. So I've listed all my outputs here. Let's talk about what's happening in quadrant 1 from 0 to pi/2. So we start at 1 and the values get smaller, decreasing to 0. So we have all those same values. We've got 1, √3/2, √2/2, 1/2, 0. What happens when we're in quadrant 2? What happens to cosine? And thinking about your unit circle, all students take calculus. S, sine is the only function. Sine and its reciprocal cosecant are positive in quadrant 2. So we know that our cosine values are going to be negative. So we are still getting those same values. It's just they've become negative in quadrant 2, and they're still decreasing. So we're going to go from +1 all the way down to -1. And then eventually we turn around, we start going back up, and we continue going back up until we get to 2 pi. So considering this graph in the same way, I've got my y values between +1 and -1. I'm going to count my quadrants, pi/2, pi, 3 pi/2, and 2 pi. In quadrant 1, we've got 0, 1, pi/6, about 0.9, pi/4, about 0.7, pi/3, about 0.5, pi/2, 0. Continuing down, 2 pi/3, we've got -1/2, then -0.7 pi/4, I'm sorry, 3 pi/4, negative √3/2 at 5 pi/6, and then over here we're down at -1. So we still have that same kind of arc, but it looks a little bit different here. So it's going to continue following that same curvature in both of these quadrants, but after we get to our bottom value at -1 pi, we're going to increase to 2 pi. So it curves back up here. It doesn't look beautiful. Let's curve it up to right there, and then it switches. It curves like this. So this is my graph of y equals cosine x. Again, we have 5 key points. So we've got 1, 0, 1. We have 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi positive 1. What is the domain of this? The domain, that graph continues off to the left and the right forever, following this same pattern. So my domain is that those inputs, or my x values, are in the set from negative infinity to positive infinity, which is all real numbers. And my range, my y values, are bounded again on this closed interval between -1 to +1. The period of cosine, we can say cosine is also periodic 2 pi. So it has a period of 2 pi. And what does that look like if it continues repeating itself forever? So I've pulled in this graph. Again, we can have it bounded between 1 and -1, and then repeating every 2 pi. So 2 pi, 4 pi, 6 pi, 8 pi forever along our x-axis. We can even go in the negative direction, such as -2 pi. So one graph of cosine looks like this, and it would repeat itself. So we get that same curve, but it's just a little bit different here. And then again, it also moves in that negative direction. All right, so it continues in both directions forever. So again, we see that domain is all real numbers, and the range is bounded between -1 and 1. So one thing we've noticed is that both sine and cosine have this period. So a function, f of x, can be said to be periodic if we can add some positive constant p such that it would still be equal to itself. So f of x plus some p value. So as we noticed, sine and cosine are periodic 2 pi. So since sine and cosine are periodic 2 pi, we could say that sine of x, well, that's also equal to sine of x plus some 2 pi value. And the same for cosine. Cosine x, that would be the same as writing cosine of x plus any 2 pi value, because that's its period, and that would be give us the same graph. We're not going to talk about tangent in this video, but I will let you know tangent is periodic. Tangent is periodic pi. So we could say that tangent x is equal to tangent of x plus pi instead of 2 pi. And we'll look at that more when we start talking about our tangent video. All right, 2 more quick things to mention about our sine and cosine functions. So now discussing amplitude. Amplitude is half the distance between the max and the min. Amplitude is a measure of height. And amplitude, since it's a measure of something, it's always positive. So if we think about our graph of sine, which we know that sine looks roughly like this, from 0 to 2 pi, and we've got a max of 1 and a min of -1. That entire distance between the max and the min is 2. So the amplitude here is 1. That means it's coming 1 up and 1 down. The amplitude of sine is 1. This is my graph of y equals sine x, as well as the amplitude of cosine, which looks like this from 0 to 2 pi, again with a max and a min of +1 and -1. For cosine, that amplitude, we see 1 up, 1 down, and 1 up again. So the amplitude of y equals sine x and y equals cosine x is 1. Now, of course, we know that graphs can have transformations. So if I put like a 3 in front of this sine, that would make my sine graph 3 times as tall and the amplitude would change. But this is like my parent function. So the amplitude of my basic sine and basic cosine function is going to be 1. One more topic. Let's talk about symmetry. And so I know this discussion has gotten long, but I think it's important for us to talk about both our sine and cosine graphs in the same video. So something you should remember from algebra, pre-calculus algebra, is odd and even functions. If a function has rotational symmetry, rotational about the origin, we call that odd. Sine is an odd function. So our algebraic definition of an odd function would be f of negative x equals negative f of x. So translating that to trig, we could say that sine of negative x is the same as negative sine of x. And considering that as a graph, if we had our basic sine graph, what we would recognize is that if I were to take this sine graph here and I were to take the whole thing and twist it on this point and rotate it about the origin, I would get a graph that looks like this, still symmetric. Okay, so sine has rotational symmetry about the origin, rotates, because it is odd. Cosine, however, is even. Even functions have reflective symmetry over the y-axis. So cosine, that's an even function. And our even definition is that f of negative x, essentially we can just drop that negative and it would be the same function, f of x. So rewriting this, we know that cosine of negative x is equal to cosine of x. So thinking about that on a graph, knowing our cosine between 0 and 2 pi looks like this, if I were to reflect that just across this y-axis, I would get the exact same graph on the other side. All right, so cosine has even symmetry. It reflects across the y-axis. Sine has odd symmetry. It rotates about the origin. All right. So that will conclude our discussion on the sine and cosine graphs. And we touched on their periods, their domain and range, their amplitude, as well as their symmetry. So in the next video, we're going to talk about tangent, as well as the other 3 reciprocal function graphs, cosecant, secant, and cotangent. As always, remember to email me if you have any questions.